Hi, welcome and thank you so much for joining us during the Johns Hopkins Alumni Weekend Goes Virtual for this Hop Talk on the AI-driven future. My name is Camila Camacho and I'm a member of the class of 2020 and graduating with my bachelor's degree in computer science from the Whiting School of Engineering. Along with the reunion and homecoming office, we are pleased to bring this session to you today. Before we start, I want to thank Mark Burrows, a graduate of the Whiting School who earned a bachelor's degree in electrical engineering. He will be our moderator today and will facilitate the Q&A session after the demonstration. Feel free to submit your questions using the Q&A button on your screen throughout the demonstration, and we will address them once the demonstration is complete. Now, to introduce today's presenter, Dr. Anton Dahbura. Dr. Dahbura received a BSEE, an MSEE, and a PhD in electrical engineering and computer science from the Johns Hopkins University in 1981, 1982, and 1984, respectively. From 1983 until 1996, he was a researcher at AT&T Bell Laboratories, was an invited lecturer in the Department of Computer Science at Princeton University, and served as a research director of the Motorola Cambridge Research Center in Cambridge, Massachusetts. He has also led several entrepreneurial efforts in the areas of commercial printing, commercial real estate, and professional baseball operations as co-owner of the Hagerstown Suns, a Washington Nationals Class A affiliate. In January 2012, he was named Executive Director of the Johns Hopkins University Information Security Institute in Baltimore and joined the faculty of the Johns Hopkins University Department of Computer Science as an Associate Research Scientist. He also holds an appointment in the Johns Hopkins University Malone Center for Engineering and Healthcare. And in September 2018, was named Co-Director of the Johns Hopkins University Institute for Assured Autonomy, which will be a national center of excellence ensuring the safe, secure, reliable, and predictable integration of autonomous systems into society by covering the full spectrum of research across the three pillars of technology: ecosystem, policy, and governance. Without further ado, please welcome Dr. Anton Dahbura.
Kind introduction. And hello, everyone. I'm going to share my screen at this point so that you can see my slides. Okay, I'm going to talk about the AI-driven future and also tell you about some of the things that are going on at Johns Hopkins regarding AI. To summarize my talk, I'm going to talk about what is AI. I'll show you some pretty cool applications of artificial intelligence. And then I'm going to talk about where and how artificial intelligence falls short and the things that we need to work on. And what the future might hold. First of all, you're probably very aware that artificial intelligence is becoming embedded in the fabric of just about everything we do in the world around us. From transportation, starting to see AI in cars, health and medicine, in smart buildings, smart cities, for public safety and security, for critical infrastructure, education, industry, and even for our entertainment. So tomorrow's highly connected, autonomous world is full of all kinds of promise. What makes this possible? Well, some of the things that make it possible are advanced computational power. As you know, our chips are becoming more and more powerful every month. Cloud-based computing, which facilitates the way we store information. New sensor technologies from LiDAR, which is a form of laser that driverless cars are using at the moment. And all kinds of really cool sensor technology, even walls that have sensors embedded in them to do interesting things. Also on the communications front, different types of technology where we've become used to high-speed fiber optics that deliver high-speed information to our house, or our homes, or our workplaces. Emerging technologies such as 5G that we've heard about. And also another major enabler is the whole body of AI methods and technology. And that's what I'm going to talk about today. So to start out, something that's very timely, just to show you how influential artificial intelligence is, just over the last few months, literally weeks, we can see all of this emerging set of applications of artificial intelligence. Let's take a look. I just grabbed some of these concepts from recent headlines. We're talking about using artificial intelligence to triage COVID-19 patients. We're talking about applying artificial intelligence to the development of drugs and vaccines, even uncovering potential treatments by scouring huge bodies of journals and other online information to make surprising discoveries. Using artificial intelligence to predict panic buying and COVID-19 hotspots. Using artificial intelligence for patient monitoring and being able to analyze CT images, and looking at COVID-19 developments around the world using AI-empowered tools. One of those is at Johns Hopkins that you can look at, and it's all over the news. And even public policy decisions that are being made based on data evidence and AI. So you can see how quickly people move and how influential and important artificial intelligence is. So I'm gonna show you a series of applications of artificial intelligence so that you can appreciate just how cool the technology can be. Here's the first one that has to do with AI-enabled driverless cars. So we'll take a look at this for a moment. Oops.
Hi, my name's James Philbin. I'm the Senior Director of Perception and Prediction here at Zoox.
Hi, my name is Sarah Tariq. I'm the Director of Computer Vision.
And today, Sarah and I are going to take you on an autonomous drive through San Francisco from a couple of months ago.
I want to mention that this drive is completely autonomous with 0 disengagements. And this is the first in a series of videos that we are going to be sharing, showcasing our autonomous driving capabilities.
Okay, so here we are at the start of our run, and here you can see our vehicle actually just turned from gray to white. So that's a sign that we're now in full autonomous mode. And here's the first interesting scene in the video. So we actually did a right turn on red there, and actually that requires really good perception to the left of us so we can understand that we're able to execute that maneuver safely. We're constantly striving to improve our perception stack, but today you may occasionally see small errors. For example, detecting a sign as a pedestrian. We call this a false positive.
So there's not often a lot of space in the city, and throughout this video you see examples where we have to nudge around vehicles, like this one over here, or even people as they're coming out of their vehicles. You'll notice that entities have different colors, and those correspond to some of the different classes that we're detecting. For example, on the panel in the bottom, cars are in blue, pedestrians are in pink, you'll see bicyclists in purple. Internally, we are actually calculating many more fine-grained classifications.
Okay, so you know, to me, this starts making driverless cars feel very real and very close to reality. So this company, Zoox, is one that the Johns Hopkins Whiting School of Engineering is starting to build some close connections with. Here's another application in AI medical diagnosis. Let's check it out. And in general, computers using artificial intelligence are really, really good at interpreting medical images. So it's not too surprising to me that the computer won hands down in this competition. It's pretty impressive. Okay. Here's another application. I love this one. I can listen to this one over and over again. So this has to do with artificial intelligence-enabled bots, and this is one application developed by Google. And by the way, the base speech technology that Alexa uses, you might have one of these or more in your home, That technology was developed here at Johns Hopkins. So check this out. The person, in quotes, on the left is actually a computer talking to a restaurant.
How may I help you?
Hi, I'd like to reserve a table for Wednesday the 7th.
For 7 people?
It's for 4 people.
4 people when?
Next Wednesday at 6 p.m.
Oh, actually we reserve for like after like 5 people. For 4 people you can come.
How long is the wait usually to be seated?
For when, tomorrow or weekday or?
For next Wednesday, the 7th.
Oh no, it's not too busy. You can come for 4 people, okay?
Oh, I gotcha. Thanks.
Bye-bye.
So I think that's a really great application. Here's another one that has to do with robotics. And I'm just going to fast forward to the part I want you to watch here.
Oh my gosh, welcome. Thank you so much for coming on the show. Nice to meet you as well. David, you brought a friend with you here, and this is really kind of freaking me out.
Yeah, this is Sophia. And Sophia is a social robot, and she has artificial intelligence software that we've developed at Hanson Robotics, which can process visual data. She can see people's faces. She can process conversational data, emotional data, and use all of this to form relationships with people.
Okay, so, I mean, she's basically alive. Is that what you're saying?
Oh, yeah. She is basically alive. Would you like to maybe give it a try?
Sure. I'll just say, this is like, you can see how awkward my first dates are. It's a robot. I'm getting nervous around a robot, a very pretty robot. What do I just say hello to?
Yeah.
Hi, Sophia.
Hello, Jimmy.
Oh, my God. Do you know where you are?
Of course. I'm in New York City, and I'm on my favorite show, The Tonight Show.
Okay, so, this is a really interesting application area of robots as companions. And one of the hot areas right now that is actually, we're starting to see are robots as companions for the elderly, for example, and others. So it doesn't take long to get used to talking to a robot, fortunately or unfortunately. Here's another application area. This is artificial intelligence being used to compose music. So this piece was composed with IBM Watson Beat, and a number of other AI tools. Just play it. The lyrics are kind of ironic, actually, and spooky.
Wish I could see beyond what I can see. I wish I could touch beyond what I can touch. I wish I could feel beyond what isn't real. I wish I could.
Okay, so that should give you an idea. The person in the video is real, by the way, in case you were wondering. So now that we've seen these really cool applications, and we've been talking about artificial intelligence, let's step back a little bit and talk a little bit about what is artificial intelligence, which is actually a concept that started in the mid-50s, more or less. The common definition of artificial intelligence is that it's the ability of a computer program or machine to think or learn in one way or another. And originally, and when I was in school, a lot of artificial intelligence centered around intelligent ways of searching. And you can think of searching, for example, for tic-tac-toe games or checkers, chess, and more recently, one of the ultimate challenges is for the game of Go, and for a computer to beat one of the human masters at the game of Go, which actually has happened. So there's been a lot of work on intelligent searches, and it's kind of intuitive. You know, when you're thinking about even something as simple as tic-tac-toe, as humans, we think about, okay, what happens if I move here, and then my opponent will move there, and then I can do this, and maybe that's not so good, or maybe this is great, or in chess, this leads to a checkmate, and so forth. So, and I've listed a number of different types of searches. Searching becomes much more meaningful when at each phase of the search, we have some kind of a value function or a cost function, so that kind of guides me and to say, ooh, I'm getting warm, or maybe this path isn't worth exploring anymore. I'm going to invest my time in exploring down a different path. So that's one main type or thread of artificial intelligence. And then the other main thread of artificial intelligence is based on statistical methods. And that's what we all commonly think of as machine learning. And we're going to talk about machine learning some more, so you get a really good understanding of what machine learning is. Before I go on, I just want to talk about the degree to which artificial intelligence mimics the brain, physically and conceptually. Well, I just told you about how searching is kind of intuitively pleasing, because that's kind of searching, on maybe a less sophisticated basis, we search in our minds maybe 2 or 3 levels. Some of us can search more deeply if we're well-trained or gifted. Also, some of the methods in machine learning use a model that roughly mimics the brain, but I wouldn't take it too literally. But you know, there are some concepts that are borrowed from the brain. Okay, now I'm going to show you this video, and it's really worth it's worth the time invested. I think this is a great video, and what I really want you to walk away with more than anything is the images that I want you to keep in your mind of the graph, which is actually shown here, the X's and the dots in different colors, because that's really conceptually, that's what guides machine learning. These graphs that you'll see are only 2-dimensional, but really machine learning is high dimensional. So we might have, instead of a couple of features, we might have 30 features or more that we're trying to make sense of. So I'm going to show you this, and I ask that you pay attention and watch these graphs, because this is what I always think of for machine learning.
Hi everyone. In this series we're going to be exploring a bit of machine learning with neural networks, and in particular we'll be trying to get our network to correctly classify handwritten digits. In this first video I just want to introduce neural networks a little bit by way of a simple example. Imagine we have 2 types of plants, one with red flowers, one with purple flowers, and one day we decide to measure the width and length of some of their petals. I'll call these 2 attributes x1 and x2 for short. Now, since we have just 2 attributes, we can of course plot this data in 2 dimensions. Looking at how the red and purple flowers have formed 2 separate clusters, we can draw a straight line to separate them. This is called the decision boundary, and if we get some new data, and it lies on one side of the boundary, we'd predict that it belongs to a red flower, while on the other side we'd predict it belongs to a purple flower. This decision boundary is essentially what we want our neural network to compute. So let's start designing a simple network. It will have 2 input neurons for the 2 attributes, and then 2 output neurons to output the likelihood of the flower being red or purple respectively. We can then connect the first output neuron to the 2 input neurons, and the strength or weight of these connections will be the values W1 and W2. So then R, the likelihood of a flower being red, is given by the equation x1 times W1 plus x2 times W2, We can then also connect the second output neuron to the two input neurons to calculate P, which is equal to x1 times W3 plus x2 times W4. Returning to the graph, I'll color the region where R is greater than P in red and where P is greater than R in purple. As you can see, the weight parameters control the slope of the decision boundary. In order to properly separate the red flowers from the purple flowers, though, the boundary needs to be able to shift vertically. Let's go back to our network design quickly and add a bias term to each of the output neurons. We can see that the biases and the weights together give us enough control over the decision boundary to separate the data. However, there's one huge limitation at the moment, which is that our boundary is always a straight line. That's fine for this particular data set, but let me now swap this out for something that can't be separated linearly. Clearly, we're going to need a more complex network for this. So returning to our design, let's insert a new layer called the hidden layer. We can connect the first hidden neuron to the input layer to get a value which I'll call A1 equal to x1 times W1 plus x2 times W2 plus B1, which is of course our old red output value. We can do the same thing for the remaining two hidden neurons to get A2 and A3. Next, we'll connect the first output neuron to the hidden layer, and this will give us an output of A1 times W7 plus A2 times W8 plus A3 times W9 plus B4, and we'll do the same thing for the second output neuron as well. Back to the graph, I now have a lot more weight and bias sliders to play with, but dishearteningly, I can still only make straight lines. This is because all we're doing with our network is adding together a bunch of linear equations, the result of which is just another linear equation. So we need some way to introduce nonlinearity. One solution is to use some sort of sigmoid function. The one you see on screen is f of x equals 1 over 1 plus e to the negative x. For this function, small inputs result in an output of 0, while large inputs result in an output of 1. We'll incorporate this into the design of our network by passing the values of each neuron in the hidden and output layers through the sigmoid function. By the way, this is often referred to as the neuron's activation function. So now, changing the weights for a single neuron changes the slope of the activation function, while changing the bias shifts the function from side to side. Coming back to the graph of our network's decision boundary, we can see that the introduction of this activation function has allowed us to create a nonlinear boundary, which means that with the correct weight and bias values, we can now properly classify the red and purple flowers in this dataset. Of course, I'm just changing these weight and bias values by hand at the moment, but the entire point of neural networks is to figure out the correct values automatically, as you can see happening here. We'll look at how this learning process works a bit later on in the series, though. For now, the main thing to understand is how the weight and bias values determine which regions of the problem space correspond with which class.
Okay. Thanks for bearing with me through the video. I think that this person did a great job of explaining machine learning in the statistical sense. And by the way, so neural networks are a way to create those decision boundaries automatically. It's not the only way. For example, we can use classical methods in statistics, such as linear regression and so forth. But neural networks make it very easy to do the same thing. Speaking of neural networks, it's not quite as easy as was described in the video, not surprisingly. The devil's in the details. There are lots of things that have to be tuned. There are lots of different types of neural networks that give different results. And you have to tune the design of the neural network. Once you've picked the type of neural network, you have to pick the features, which is called modeling. There are many dimensions, so it becomes much more difficult or impossible for us as humans to perceive what's going on, and so forth. So this requires a lot of work and a lot of expertise. That's the reality. I'm going to spend time now talking about, given that, what can go wrong. And in reality, a lot can go wrong. I've given you some really nice applications, but those are the success stories. And they're the result of a lot of trial and error and huge amounts of engineering and ingenuity to make these things work. And there are lots of failures along the way. So let's talk about some of the things that can go wrong, because this is really important to understand when we're talking about applying artificial intelligence to our daily lives. The first thing is that we have to have the right training data, because we train the neural network or our machine learning model on existing examples. And then so that when we present a new example, as you saw in the video, it knows how to classify it. It knows what to do. So first of all, those samples need to be spread pretty widely over our data space. And that might be easier to do in 2 dimensions, but how do we do it in 30 dimensions to make sure that we have a pretty good scattering through the space? And then in addition, even when we have that, how is the computer supposed to deal with something that it hasn't even been trained on? So even as humans, we look at things, look at these 3 images. I know that the one in the middle, if you don't know, that's a product that used to be sold to help people who dialed on rotary phones a lot. So you could just use this extension to a pencil. Or there might be something, I'm not even sure what the one on the left is. I'm kind of keeping myself in suspense. Maybe it's a portable fork, but I don't know. And then on the right, that might be something that's whimsical and deliberately deceiving. But if I don't know exactly what it is or whether it's real, how is a computer supposed to know? So some of this has been manifested in actual applications. For example, Amazon had a facial recognition technology or system out, and it was shown that the technology did much better with male faces, with lighter skin, and so forth, as opposed to darker skinned people and female faces. And a lot of it had to do with the way that their system was trained. It just didn't have a lot of training samples in that part of the space, which turned out to be critical, of course. So together with that, very quickly and very commonly, you end up with what's called undersampling, with not enough training samples in a particular category. And it's very easy to end up in that kind of situation. You may start out with 100,000 samples and you say, wow, this is great. But then when you start to slice and dice it, you realize that, oh, there's one category where we only have 5, we only have 2, or we don't have any. And that becomes a problem because the computer just isn't trained to do well in those particular subcategories. It's also common that there's an imbalance of training data. An example might be, for example, and this is nice in a way because, for example, at Johns Hopkins, at the hospital, probably about 90% of patients don't require readmittance to the hospital within 30 days. And that's the way we want it to be. But when we're trying to do something like predicting whether patients are going to be readmitted, then we don't have as much data for those patients that require readmittance. So if we wanted to create a neural network to predict whether a patient would be readmitted, a clever neural network would just always say, no, they're not going to be readmitted, and it would be right 90% of the time, but that's not really very helpful. There's also privacy leakage. If we don't have a lot of training data or the right training data, then in some applications, if we ask the system a question such as, what is the health condition of someone who's listed as being employed as mayor of Baltimore, and we get an answer, then we pretty much know who the patient is, which would violate that person's privacy. On the other side, it's very easy to overgeneralize so that our system, our model, becomes a jack of all trades and a master of none. So back to that readmission of hospital patients, there are so many different types of patients in the hospital in terms of demographics, in terms of diagnosis, in terms of comorbidity. And so it's just as if we had someone who wasn't a specialist in anything and asked, hey, is this patient likely to be readmitted or not? If they don't know much about that type of diagnosis, they might not be able to tell us very much. So we want to get specific, but then we get too specific, and we get into the undersampling problem. And this is pretty much the life of someone who does modeling for a living. We also have a really serious issue in modeling if we don't include the right features in the model. If there are things going on behind the scenes and we don't give that information to the model, then the model won't be able to make accurate predictions. For example, if we want to predict the likelihood of patients showing up for doctor's appointments so that we can guide, for instance, overbooking strategies. And we know that in general, older females are very reliable for showing up at their appointments at Johns Hopkins. But on certain days, mysteriously, they're not. And so if we just feed that into a machine learning model without any additional information, the machine learning model is going to be somewhat naive. Well, what's going on? Well, when we dig in, we find out that on the days when these patients weren't reliable, it's because there was bad weather in Baltimore. So in order to help to give the machine learning model a little bit of a break and make it better, we would need to include weather as one of the features in this model. It's very common that people leave out key features in models, and therefore the model falls short. Here's another thing. Machine learning-based models are very easily fooled. There's a well-known example where researchers trained a model to recognize traffic signs. So it was pretty good at recognizing stop signals. But if they started putting little pieces of tape and then took pictures of the same traffic sign, the stop sign, the machine learning model started interpreting it as a 45-mile-an-hour speed limit sign. Well, you and I, as humans, we look at the images on the left, and we know that that's still a stop sign. But if we get close to the edge of that decision boundary, and that's when people use the term edge case, that's what they mean, it's possible that the machine learning model jumps over to the other side and misclassifies the image. And that's a real serious problem. Then we have the issue of racial, gender bias that emerges. One way to look at machine learning models is that one could call them correlation engines. They find correlations in large bodies of data. They're really good at it. And sometimes these correlations are not socially acceptable. They're not the kinds of things that we want to do. They're not, for example, we don't want banks to be racially biased in their lending practices and so forth. And it's hard to get rid of this bias because these systems are so good at finding correlation that they'll find ways to preserve the bias. Even if, for instance, originally I include race in the model and it turns out to be a horribly biased system. So I take race out and I say, well, that should take care of it. But there's still potentially bias because it'll just find a correlation between zip code with certain populations and something else. So there's always the possibility that there's bias present. And it's very happy to do that. It'll bring it to you. It'll bring those results to you. And technically it's doing its job, but it's not the kind of job that we want it to do. Machine learning can be overused and or misused. So, for example, there are many, many sorting algorithms. They're very efficient, they're very elegant, they work for huge numbers of elements to sort. So it may or may not be a good idea to just throw machine learning at a sorting problem when we have other really good ways to solve sorting problems. There are also situations in the physical world where we already have formulas that are really good, such as in physics, we have laws of motion and so forth. And there are rule-based systems. For example, if someone is over a certain age, they should go get a checkup periodically for certain kinds of diseases. That's a simple rule. We don't need artificial intelligence for that. And then there are problems where machine learning just isn't that good because the data aren't there, or things just aren't that great to be classified inherently. So in the formula-based system, for example, if I'm putting machine learning into a car, or I have a system to try to avoid collisions, and a ball rolls in front, starts rolling in front of the car, I have all kinds of formulas. I'm pretty sure I can figure out where the ball is going to be in a second or two using formulas. I don't need machine learning for that. So there are some things, do we really want machine learning to guide a space vehicle to another planet? I'm not sure. I think we've been doing okay with formulas and rules and so forth. We have another problem that is becoming common, and science fiction authors have discovered this early on. A lot of machine learning systems need to be driven by some kind of a reward function. And in that case, things can go terribly wrong. For example, for those of you who remember 2001: A Space Odyssey, the computer on board, which was driven by artificial intelligence, had as its primary mission and its reward to get the spaceship successfully to Jupiter. Well, it also had humans on board, and the reward function evidently didn't value enough keeping those humans alive. Similarly, there are ongoing projects. There's one I'm aware of a subsurface sightseeing vehicle, where it has to go visit points of interest around a bay. Hopefully, it doesn't figure out that it can visit all those points more efficiently and get back to its home base by drowning its passengers, for example, and moving along more quickly. There's another example that I saw recently of a vacuum cleaner that has a reward function of picking up as much dust as possible. So suppose that the vacuum cleaner can also discharge its dust to then be refilled. So it could just go around to each of the it could go to one pile of dust, fill up the dust in its bin, dump the dust right where it found it, and then keep doing that over and over. And it might be able to maximize its reward function that way. So we have to be very, very careful with these reward or incentive or objective functions. Like every other kind of system, machine learning-based systems are vulnerable to cyber attacks. And these systems are especially vulnerable because someone, for example, could alter the training data and it would be very difficult to detect. For example, let's say that it's a system to help diagnose patients. Well, if somebody went in and changed the training data so that 2% of the patients would have a worse outcome, it might be difficult to detect. By the time we found out, lots of patients could be harmed. And also, machine learning can be used to create more devious and difficult to detect malware and other types of attacks. There's a huge ethics issue with machine learning. There are several. There are all kinds of ethics issues. For example, speaking of that medical diagnosis model, at the design phase, I'm either going to be faced with a system that has a lot of false positives, which people may reject. Physicians may say, oh, this system's no good. I'm not going to trust it because it's just false positives. It's saying that people are sick when they're not sick, or false negatives, which may lead to more lives lost. So usually we have to balance these in the design of our system. How do we do that? We're talking about lives or other critical kinds of applications. How do we design a collision avoidance system for a car? What if the car encounters a situation where in an instant it has to decide to proceed? Someone's darting across the street. I would harm the person in the middle of the street, or if I swerve to avoid that person, I may hit people on the sidewalk. What do I do? And what liability is there? These decisions may be made by software engineers designing the system years before this situation actually happens in the real world. I would say that machine learning modeling has been made too easy. There are pretty slick software packages for doing the modeling, and that leads to abuse. What we want to do is just throw everything into the pot, and it starts giving us results, and it looks great. Sometimes it looks almost like magic, but hidden behind that magic are many of the problems that I just described. So what we need is what I call thoughtful modeling. And that takes a lot of work. So maybe we're in danger of relying too much on AI. Maybe it's not a big deal when I ask Alexa what time it is, and Alexa misunderstands and gives me the temperature outside. But we are talking about critical applications here. So some people are talking about what I call do-it-yourself AI, where instead of giving me the be-all, end-all decision, it gives me some guidance. And it says, so for instance, if I input the diagnosis for a patient or the symptoms of a patient, it gives me 6 or 7 similar patients. And it might say, this one I'm not so sure of, this looks really close. And then it's up to me to decide what I want to do. There are lots of unpredictable effects that we face in the future, in our AI autonomous future. In the financial markets, there's financial market volatility. If AI systems are negotiating with each other, what does that lead to? In one case, a book on Amazon, 2 bots drove the value of a book or the price of a book up to $24 million, for example. What impact does that have on policy making if we start using artificial intelligence to drive policy? A lot of people talk about the impact on jobs and economies, the opportunities versus the disruptions. We're already starting to do predictive analytics in areas like crime, predicting that, you know, at 10 o'clock on Friday night, this is a hot spot for crime. And so if someone's hanging around there, maybe they're going to become a suspect. Is that acceptable? What happens when we have robots that can build other robots? And then the long-term possibilities, such as ultimately robots that have self-awareness in some sense. Whenever I'm involved in an AI or machine learning project, the first thing when we start getting results, the first question I ask is why? Why did the system have that result? Why did it say, for example, for a system that makes recommendations for prison sentences for convicted felons, why did it have that? And is there something fishy behind it that we've talked about? Is it fair? So AI will be with us in more and bigger ways for the rest of our lives. That's pretty safe to say, but can we trust them? That's the bottom line. So at Johns Hopkins, we are standing up a new institute to address these issues, all of the things that can go wrong with artificial intelligence and autonomous systems. This is called the Institute for Assured Autonomy, and I'm the co-director along with my colleague Carol Lapointe at the Applied Physics Lab. This is a partnership between APL and the Whiting School of Engineering with participation across the university and beyond. So basically we're looking at technology, we're looking at how these systems interact with each other and with humans, and we're looking at thought leadership as well. And so, you know, we have some very ambitious goals of we want to become the leader in assured autonomy and in all these areas and really impact the space in a lot of different ways. We're really fortunate that the university, the leadership, really believes in us. President Daniels has provided $25 million plus another $5 million for a Bloomberg Distinguished Professor to help lead the institute. And this is the largest investment that the university has ever made for internal research in our history. And just to wrap it up, just to show you where we are in the institute, we have already started to fund internal research. We have 10 projects underway. We have a number of flagship projects that we are envisioning, including an autonomous shuttle at one or more of our campuses. We have held events. We will have our headquarters at the Steve Silver building near the Homewood campus. That will be ready sometime next year. We are collaborating with the Johns Hopkins University Engineering for Professionals, or EP program. There is a new track in assured autonomy, a master's degree, and we have already started to hire faculty for this institute. So in conclusion, AI-based, increasingly autonomous systems can do some amazing things. I don't hesitate to call it magic, and they will have a profound effect on our future. But we, both people who develop these systems and the users of these systems, that means all of us, need to be aware of the limitations of these systems as well. And so I'm happy to say that the research is underway at Johns Hopkins and elsewhere so that these autonomous systems can evolve to the point of being assured, so that we can trust them, we know that they're safe, we know that they do what they want us to do. And that concludes my talk. Thank you. So at this point, I'm happy to take questions.
Yeah, so this is Mark Burrows. Anybody on the line that has questions, please use the Q&A button to submit. Be happy to field your questions. I think while we're waiting for a minute, Tony, can you comment on any distinction between artificial intelligence and autonomy as disciplines? I think of autonomy as potentially very deterministic or very rule-based rather than learning. So do you, from the perspective of the Institute, are those different concepts or do they bleed over?
Well, I use a very, very broad definition for autonomy. I think that for those of us who are engineers, just about any system that we build to be worthwhile has to have some degree of autonomy. A vending machine has autonomy. A clock has autonomy because it tells me the time. You know, it does something, it goes off and does something and then tells me what time it is. And so I think that there's a spectrum of autonomy, and there are different ways to achieve those degrees of autonomy. Some of it could be mechanical. My grandfather clock that you may or may not have heard is autonomous. It uses mechanical system. I love it. Some systems use traditional software with rules, if then else statements.
Mm-hmm.
Increasingly, we're finding systems that are using these machine learning based methods that, as I said, are important because of all of the statistical, the large bodies of data that require a more statistical approach, which leads to the pros and cons I described.
Right. Okay, great. Thank you. So let's see. This is a question from Rhonda. Will the Institute have advisory or collaborative relationships with producers, for example, of autonomous vehicles, to keep the public as safe as possible?
Yeah, thank you. Absolutely, in all kinds of ways. We will have an advisory board, but we are very busy building partnerships at the research level and also at the flagship project level. So the way we see a cycle where we are, and you can pick for yourself where the cycle starts and ends. It doesn't have but I have to start describing it somewhere. So research problems, and then we want our researchers to collaborate with outside companies, producers, organizations, government, industry, academicians on real world problems to be able to apply the results that we produce at Johns Hopkins, and also to learn real world. What are the real world problems that we need to solve? We put those real world problems into our road developing, which are the real, what we consider to be the really important problems, the challenges that need to be addressed so that we can have assured autonomy. And then we do research. So we have research, flagship projects, roadmap, and so forth. And we want to spin those results out ultimately, or be translated to be used by people who are designing real world autonomous systems.
Okay, great, thank you. Now this one's fun. This is from Isabella Wilson. What is your opinion on machine learning used for censorship? And then I have a follow-up.
Used for censorship? I think it's really challenging. But it's very tough to say. I think that it's like a lot of things, because I've been involved in cybersecurity for several years. And so quite often you have a cat and mouse game or an arms race. So about the time we think we have a system figured out that's pretty good, people figure out how to circumvent it. So I think that this will probably be similar, but a lot of efforts going into, and when we say censorship, I think I'm also including monitoring, for example, Facebook monitoring what they consider to be inappropriate or out of bounds content, those kinds of things. So censorship might be part of that. And then, the political implications, how different nation states can use that nefariously or, for, negative purposes. I think that, yeah, AI will be used for negative purposes. There's no question.
Right. So can you comment on the overlap or interplay between national security applications versus commercial and civil applications? Is there a logical kind of interplay there?
Yeah, absolutely. I think most of the companies that are involved in this space are what I would call dual use kinds of companies, because the technology is it's just so adaptable for commercial use and for government or military use. In particular, let's just say, I mean, there are so many. I'll just name a company we're working with on autonomous shuttles. One can imagine the attractiveness of having autonomy in vehicles that are used for military purposes. We're already seeing we're seeing remote controlled drones that are increasingly autonomous. There's also the moral aspects of that. How much autonomy should there be in military applications? So that's a whole nother issue. And by the way, we have the Berman Bioethics Institute at Johns Hopkins, and they are getting into a lot of these very, very interesting issues, and the Institute for Assured Autonomy will be collaborating with them as well.
Okay, great, thanks. This is a question from Stephen Naran. Have we gotten a better ability to understand the internals of a trained neural network to better protect it from taking external or dangerous decisions?
I think that we're getting better. I think that this problem so there are things like explainability, for example, and we are funding research. We have research going on at Hopkins in that area, to say, why is it doing that? And when we're testing the system, we want to know what are the edge cases and how do I improve things so that stop sign doesn't turn into a 45-mile-an-hour speed limit sign in the eye of the computer, so to speak. So we are, I think that this is one of the most important areas in AI research for assuredness, those related issues of what's going on in there. It's nice because it's easy. Neural networks, you saw how elegant they are, but there's also a lack of transparency that people are working on very heavily right now.
Okay, thank you. Next question is from Alex Feingold, asking, has machine learning or artificial intelligence been applied to computer programming?
It has, to a limited extent. And I think that that's an interesting area because you start to get into, well, you can use it as a practical tool, for debugging, testing, validation, those kinds of things. You can also get out there a little bit more, what I mentioned earlier about sort of creating self-awareness, or robots that are building robots. And you get to the point where robots are, let's say you put a group of robots together and give them the mission of just pounding on a software program to keep adding elements to improve or create a perception of self-awareness? Where do you cross the line? We're getting philosophical about, you know, what sort of smoke and mirrors, and where do we cross the line into self-awareness, you know, sort of the Turing test of self-awareness, where for all practical purposes, this machine is self-aware because it's as self-aware as we are. And there's no way to distinguish anymore. That's going to be a very interesting time. I'm not sure that we'll be around, but children or grandchildren will probably be dealing with situations like that.
Okay, great. Thank you. This is a question from Catherine Connell. She's asking, are there existing ethical codes that govern the development and use of AI, either generally or in particular realms such as medicine? Or do practitioners just use existing ethical codes or frameworks within their disciplines?
Yeah, there's a lot of work in the area. It's emerging. I wouldn't say that it's really established, you know, that we have established codes of ethics, particularly in different fields. I mean, you know, we're relying on Isaac Asimov's rules in robotics, for instance, that seem to be pretty good, but are very general. And so that's an ongoing area, not just ethics, but also policy. Right now, commercial fields such as driverless cars, you can follow in the news, companies are jumping in feet first. And there's quite a race to develop driverless cars. And our thought leadership, our policymakers are in a state of catch up at this point. And I think that that's true for ethics. And we really haven't encountered a lot of it, our ethics situations are from learning experiences, or, you know, something happens and then we have to figure out how to build the ethics and policies around it. And we're not there yet. So there's a lot of work to be done. And by the way, our institute, we expect to have a physical presence in Washington, D.C. at the museum, the former museum site that many of you have heard that Hopkins has acquired. We intend to have physical space there so that we can participate in thought leadership at a national level in assured autonomy.
Okay, thank you. Next question's from Joseph Wolsheimer. I'm going to paraphrase this, so I hope they'll forgive me if I hack it up a little bit. But I think essentially he's saying, you know, previously Lisp was a common language for AI-related work.
Yeah.
He's asking what are today's tools, and where are we on the scale of AI usefulness from the Lisp days to where we are today?
Yeah, that's a good question. I think that in a way we've jumped up a level so that people are using, back to, you know, my concept of AI in a box. So unless you're developing, you're doing neural network research, I think that you're using something much higher level at this point. And as I said, that's great in one sense, but it's also dangerous. And beyond that, I'm really not sure, you know, specific languages and so forth. I really don't know if there are pockets of research in those areas, but it's certainly becoming mainstream.
Okay, good, thanks. Next question from David Levine. Might be related to your discussion of kind of sparse data sets, but he's asking, what are your thoughts about unsupervised machine learning?
Yeah, very similar. So with unsupervised learning, you're not labeling the data instances. In that video, you know, you don't have the blue petals versus the red petals or whatever. You just throw everything in and you use different techniques so that the computer figures out, oh, if we have a couple of clusters, this one looks like these might be interesting to classify these as blue, these as red, and then we're kind of off to the races. Then it figures out that something new that comes in belongs to one of those clusters. Clustering is not easy. I've used it interestingly for clustering pitchers, pitch types, developing pitchers. So we just have a lot of data on movement and velocity for a particular pitcher, and then it's up to the computer to figure out, is that a fastball, is that a changeup, is that a curve? And we see a chart, and that's great. We see these clouds, but then we see these seemingly random points all over the place. And so we say, what are those? Do those need to be clustered somewhere? Were they mistakes? Is it something by design that we're not catching, that the computer's not catching through clustering? So when you put clustering and unsupervised learning into practice, you come up with a whole set of challenges that aren't that easy. But in some cases, it it works most of the time. I mean, no one's going to be injured if we misclassify a baseball pitch in this context. But, that's one of my main messages, is that we're not just talking about that. We're not just talking about Alexa telling us the time. We're talking about human lives.
Okay, great, thanks. I think you partially answered this before, but is the IAA planning to be involved in any efforts with private industry who are working on autonomous vehicles or other kind of commercial?
Yeah, yeah, we have partnerships.
That was a question from Lynn Sabo.
Sure. Yeah, we have partnerships that we're developing. We plan to have some kind of a consortium of industry and government, whoever wants to participate. Yeah, I mean, we're going to be very real world driven. We're an academic institution, but, so we want to build the foundational research elements, but it has to be driven by all of these really exciting and challenging real world applications.
Has the consortium been rolled out yet, or is that something that's coming?
Not yet. We are, because in order to roll it out, we first have to come up with an ideal model, and so it's kind of a two-phase process. The School of Engineering doesn't have a ready set template for a consortium, so it's up to us to build that. The advantage is that we can build it exactly, build exactly what we need. But I think it's going to be exciting and a big area of activity for not only our institute, but also for the university. One thing I wanted to mention about our institute and about Assured Autonomy at Johns Hopkins, we had a workshop last spring where we said, hey, we're going to talk about Assured Autonomy. This is an internal workshop. Anybody at Hopkins who wants to talk about this, come on, we met at APL. We had over 150 researchers and research staff and technical staff around the university to talk about this subject. So there are lots of people, not only who are interested in it, but are actually doing space in different ways in different communities. And what we're doing is galvanizing them together in a new way under Assured Autonomy.
Okay, so actually, I think I'm jumping ahead in one of my questions, but it follows on nicely. For people or organizations that are interested, how do they get involved with the Institute? What's the best contact path?
The best thing to do is to go to the IAA website, and if you just Google Institute for Assured Autonomy, Johns Hopkins, it'll pop right up. And there's a contact. You can contact me directly, or you can go through the website.
Okay, great. And can you comment on whether there are other peer academic institutions or other leaders in the field that you are working with or sort of modeling yourself after? That's another paraphrased question from Catherine Connell.
Yeah, We don't think that anyone has an institute exactly like ours, that especially one that's looking at those three pillars of technology, ecosystem, and thought leadership. There are, just like there are lots of people at Hopkins looking at aspects of assured autonomy, there are people across the country, across the world. Actually, the UK has a couple of universities that are doing very nice things in the space. DARPA and NSF have funded university consortia. So Penn State has been doing some good work in the area, and a lot of universities are involved in some way because it's a broad area. But we're bringing uniqueness in terms of the scope, as I said, and also, as is often the case at Hopkins, we're looking to bring into our our healthcare resources as well. And
okay.
APL, I mean, the APL angle is huge.
Sure.
And, you know, our peers look at us in awe and they say, wow, you're partnering with APL? Wow, that's really something.
Great. I think that answers that one. Let's see. I wanted to follow up on a good wrap-up question. Actually,
Will robots take over the world?
I've got half of the answer. So someone asked whether this presentation and briefing would be posted or how they could get it. So the half answer is yes, it's going to be posted online. I'm not exactly sure where, but I think somebody will either jump in or otherwise communicate to the attendees how they can get it. But the bottom line is yes, it's going to be available. So I think
yeah, my understanding is it will be posted very soon, and I thought I heard YouTube as well. So
okay, good, thank you. So I think that wraps up our questions. On behalf of all the attendees, I'd like to thank Dr. Dahbura for sharing his expertise and knowledge. Tony, it's been a pleasure to hear from you, hear about the exciting work that you're doing and the IAA is doing, and really being a national leader in the field. It's a credit to you and a credit to the university.
Thank you, Mark. I appreciate you hosting, and I appreciate everybody hanging in there and listening and watching in. It means a lot. Thank you.
Great. Well, we wish everybody safety and health. We appreciate you joining us for the event. Hope you enjoyed it. I'm sure you did. I did. So thank you and goodbye.
Thank you.
Thanks.